Okay, so we're going to continue chapter 2. And we left off, we had just talked about ions and ionic bonds. So we'll review that in a little bit later. But I want to talk about another way that different atoms can react. So remember, a lot of the ways that atoms will react is based on this chart. This is electronegativity. So the more electronegative an atom is, the stronger its attraction to electrons. So we talked about last time things like sodium, which has a very low electronegativity, and chlorine, which has very high electronegativity. Sodium will actually give up its electrons and chlorine will take them. So that's one way atoms can react. Now let's look at two that have much more similar electronegativity. So here's carbon and hydrogen. They both have electronegativities that are pretty darn similar. When atoms have pretty similar electronegativities, one of the ways they can interact to make themselves more stable is through something called a covalent bond. And a covalent bond is a sharing of electrons between two atoms. So here's carbon. And carbon, which has an atomic number of 6, has how many electrons on its outer electron shell? And that's something to review as well. It has 4. So remember, there's 2 on the inner shell, and it has 4 purple dots here on the outer shell. And that outer shell can hold up to 8 electrons, so it's missing 4. Hydrogen has 1 electron on a shell that can hold up to 2. So each hydrogen is missing 1 electron. So when carbon and hydrogen interact, carbon and hydrogen can share electrons. And if they do that, they can look something like this on the right here. And each carbon, or the carbon, is sharing 1 electron with each hydrogen, so that each hydrogen is now interacting with 2 total electrons. And if you count the number of electrons that the outer shell of carbon is interacting with, it's 1, 2, 3, 4, 5, 6, 7, 8 total. So now both of them are stable. So they share electrons to fill each other's valence shells. So kind of, if the analogy for an ionic bond is you as a student have 2 textbooks, someone else in the class has no textbooks, so you're unstable because you're carrying around 2 textbooks and you don't need to, and they're unstable because they don't have any. You give away your textbook, one of the textbooks, and now both of you have one and you're both happier, right? Analogy for a covalent bond is you have half a textbook, someone else in the classroom has half a textbook, so neither of you is happy because you only have half the information. You come together and you share your halves. You now have 1 whole textbook between the 2 of you, and both of you are better off. So the big difference between the two is ions can separate, and they're just as stable as they were when they were attracted to each other. So an ionic bond is actually fairly easy to break and reform. It'll break apart and come back together. Covalent bond, these atoms are only stable when they're together. If you break them apart, they're both going to be less stable. So it's going to take a lot of force to break them apart. So covalent bonds, incredibly strong. These are the strongest bond that we're going to see in this chapter, our covalent bond. So covalent bond means sharing of electrons. Okay. All right. So some atoms make more than 1 covalent bond with each other. So here's 2 oxygen atoms, and if I draw these out of myself, oxygen has 6 valence electrons. So how many electrons more does it need to fill its valence shell? It needs 2 more to fill its valence shell. That was kind of a weird sentence, but okay. So if you have 2 oxygen molecules next to each other, they each need 2 more. If they form 1 covalent bond, if they share those 2 electrons, they're each only getting 1 more electron. What they can do is they can form what's called a double bond, and they're now sharing 4 electrons between them. You can draw it this way, it can be drawn this way. And now if you count the electrons that are interacting with this one on the left's a valence shell. It's 1, 2, 3, 4 of its own, and 1, 2, 3, 4 that it's sharing. That's 8 total. And same with the other one. So this would be a double bond between two oxygen molecules. This is a drawing of oxygen gas, or O2. O2. So something that you're going to see, and I don't think I've mentioned so far, a lot of these covalent molecules or covalent compounds that we see, you'll see numbers next to the letters. The numbers mean how many of that atom there are. So in oxygen gas, there are 2 oxygen molecules. The one on the last slide was CH4, which means there's 1 carbon and 4 hydrogens. Don't try to look up CH. It doesn't exist there. Right? You may not have noticed this, but if you look at all these elements, they all start with a capital letter. If they have more than one letter, the second letter is lowercase. So chlorine has a capital C and a lowercase l. Sodium, capital N, lowercase a. So if you see 2 capital letters next to each other, that means it's 2 different atoms. Okay, I want to... All right, we've done the first 2. Well, I've showed you the first 2. So try number 3, and we'll do that. And I'll give you a minute maybe to try drawing number 3 here, and then we'll do it as a class. And you can go on to number 4 if you do pretty well. There's many different ways to draw these. You can overlap their valence shells. You can draw circles between them. Actually, I should have left that up. Okay. So, big picture, sharing of electrons between atoms. So 4 electrons being shared between carbon and oxygen, 4 electrons being shared between this carbon and this oxygen. You count up the number of electrons carbon's now interacting with on its valence shell. 1, 2, 3, 4, 5, 6, 7, 8. It's full. Count up the number that oxygen is. It has 1, 2, 3, 4 of its own, and 1, 2, 3, 4 that it's sharing. We're going to get to in a few, maybe not today, but probably on Friday, we're going to talk about bond potential of different atoms, and you'll learn at that point that hydrogen always makes 1 bond, 1 covalent bond, oxygen 2, nitrogen 3, and carbon 4. We'll get there, and that's something that's pretty consistent. H2O, if I was to draw that, hydrogen has 1 valence electron. Oxygen, again, has 6, so it would need, you could bond it like that, right? So hydrogen making a single bond to oxygen, this hydrogen making a single bond to oxygen. Now oxygen's making 2 bonds total, and they both have full valences, right? Okay. So covalent bonds, very, very strong because it's a sharing of electrons between atoms. Okay. Questions? Any questions on covalent bonds so far? Sharing of electrons, ionic bonds, electrons are being transferred. Okay. Okay. So this happens, covalent bonds typically happens when electronegativity is fairly similar, but there's a range. Atoms can have exactly the same electronegativity, so 2 oxygen atoms have exactly the same electronegativity, or atoms can have fairly dissimilar electronegativities, like hydrogen and oxygen. Now, it's not so dissimilar that they are going to form ions, but it's dissimilar enough that they're not going to share those electrons equally. So we can think of this as a continuum. You have a purely straight-up covalent bond where the 2 atoms are equal, and they're going to share these 4 electrons between the 2 oxygen molecules very evenly. This is what we call a nonpolar covalent bond. It's when atoms share electrons equally. An ion is the other end of the spectrum. So when sodium and chlorine come together, they share so dissimilarly that sodium gives up an electron and chlorine takes it. Right? Somewhere between that is something we call a polar covalent bond. So it's still a covalent bond. It's still a sharing of electrons, but there is now an unequal sharing of electrons between the two atoms. And a prime example of this is water. Water, we have oxygen and hydrogen. They have fairly dissimilar electronegativities. Oxygen is more electronegative than hydrogen. They're not all that different in size, but oxygen has a lot more protons than hydrogen. So these two electrons that are in this bond between hydrogen and oxygen spend more of their time on the oxygen side. It's not to the point where oxygen takes it away and hydrogen becomes a positive ion and oxygen becomes a negative anion, but it's to the point where the electrons are spending so much time on the oxygen side that it becomes what's called partially negative, and hydrogen becomes partially positive. So remember the ions, we just said positive or negative. This little symbol means partial charge. So polar covalent bonds lead to partial charges. So if you look again, it's the oxygen 3.4, hydrogen 2.2. They're fairly dissimilar, so the electron share between hydrogen and oxygen will spend more time on the oxygen side than on the hydrogen side, and that leads to what's called polarity. So polar covalent bonds result in partial charges. Oxygen is partially negative. The hydrogen is partially positive. This is one of the most important things you'll get out of this chapter, is understanding what this word polarity means, because it's going to come back throughout the semester. So do you understand what polarity means? It's a kind of a hard concept to get at first. So it's somewhere in between an even sharing and an ion, where these electrons are more attracted to the oxygen than they are to the hydrogen. So oxygen becomes negative, hydrogen becomes positive. Okay so far? Okay. So think about this now. What will happen when two water molecules interact? So which of these four scenarios do you think is likely to happen when two water molecules come close to each other? Okay, last few responses. You're doing well. Okay, good. So about 70% of you got this right so far. So think about this. So here's two water molecules. I'm not going to draw all their electron shells out anymore. It's really tedious, so I don't want to do it. So in water, you have unequal sharing, so it's polar. So what's the charge on oxygen? So it's partially negative because it's pulling the electrons towards it. What's the charge on hydrogen? Partially positive. So you've got these partially positive and partially negatives. So the second most popular answer was B, which says the hydrogen from one molecule will be attracted to the hydrogen from the other molecule. Is that going to happen? All right, they're both positive charges. And just like ions, positive ion is attracted to a negative ion, a partial positive charge is going to be attracted to a partial negative charge. So the hydrogen is going to be attracted to the oxygen like this. So C, the oxygen from one molecule will be attracted to the hydrogen from the other molecule. That's the best answer. Right, and that's what, most of you, 70% of you said that. So good job. So C, you're going to get an attraction between the two partial charges. This attraction, when polar molecules are attracted to each other, is something called a hydrogen bond. So this attraction between hydrogen and oxygen is a hydrogen bond. So partial positive charges are attracted to partial negative charges. So that happens between two water molecules. So the word hydrogen bond can throw people off. I say, what is a hydrogen bond? They say, oh, it's a bond that involves hydrogen. Well, usually it does, because hydrogen is often involved in polar molecules. When hydrogen is attached to oxygen, it causes polarity. When hydrogen is attached to nitrogen, it causes polarity. So hydrogen is a pretty weakly electronegative atom. It's going to often be in these polar interactions. But really, a hydrogen bond is any time two polar molecules are attracted to each other. It's the attraction between the charges on polar molecules. So the attraction, hydrogen bond is the attraction between charges on polar molecules. So it's the partial positive attracted to the partial negative. Okay? You following me so far? This is hugely important. Basically, the rest of today, we're going to be talking about what this does to water, because a lot of the stuff that properties that water has is due to hydrogen bonds. And if you're in my lab, you might have heard this yesterday. Okay. So water molecules aren't just attracted to each other; they're attracted to anything that has a charge. So water molecules are going to be attracted to other polar molecules. So here's ammonia. Ammonia is attracted to water molecules. Water molecules are also attracted to ions. So here's a sodium ion. What part of the water molecule is sodium going to be attracted to? Yeah, to the oxygen. So sodium's positively charged. The oxygen is partially negative. They're going to be attracted to each other. Exactly. Okay. Okay. All right, there were a few more. I think I put them in your slides, a few more clicker questions. You can work on those on your own. I'm going to skip by them because I want to get to water today, and I'll have some more questions in water as we go along. So this brings us to water. Water is hugely important to biological organisms. Water is essential to life for many processes. We're going to see, as we go through the next few chapters, all the different things that water is involved in, and water being present is just a given in a lot of reactions. Most cells are surrounded by water and made up of about 70 to 90% water. Just think about if you go for a long time without drinking water, how bad you feel. This is, your intense need for water is so high. It's the abundance of water on Earth that is one of the main reasons that we can live here, that life exists here. And when scientists look for life on other planets, one of the main things they're looking for is water. So one of the explorations to Mars, they actually, I don't know if you remember this, it was a few years ago, they crashed a rocket into Mars, and then they had another rocket that came behind it and measured what was kicked up by that rocket. And what they were doing is they were looking for what molecules were kind of exposed by crashing into Mars. And one of the main ones they were looking for was water. And there being water on Mars would mean that life could possibly exist in a similar form as to the life we have here. So water, very important for life. one of the reasons is what we just talked about, is that water is polar. Oxygen has a partial negative charge. The hydrogen atoms have a partial positive charge. So water is polar, and thus water forms hydrogen bonds. So this is all kind of review from 2 or 3 slides ago. But since polar molecules are attracted to other polar molecules, water is attracted to anything with a charge, including itself. So polarity of water gives it a lot of properties that make it versatile, very useful, and a lot of the properties that make it essential to life on Earth. And we're going to talk about a bunch of them today. So here's a list of the different properties. We're going to go through each of these and talk about what I mean by it and why it's important. So cohesion is going to be the first one. Water is a versatile solvent. Water moderates temperature. Water expands upon freezing, which is unique. It's different than most liquids. And it's a key participant in many chemical reactions. Often it's essential to many chemical reactions, including the chemical reactions that allow us to extract energy from, well, plants to capture energy from sunlight, and it's also a participant in the reaction that we use to extract energy from our food. Okay, so cohesion, versatile solvent, moderation temperature, expansion upon freezing, and chemical reactions. So we'll see how many of these we get to for the rest of today. So cohesion, or cohesiveness, is simply the property of water that it sticks to things. The word cohesion means that water sticks to itself, and the word adhesion is kind of related to this, is that water sticks to other things. So water tends to stick to itself, water tends to stick to other things. And if you haven't done the second lab for 1010, you will get to explore some of these. So water tends to stick to itself. We've experienced this throughout our lives. If you've ever used a straw, this is one of the things you've exploited. So you suck on a straw, you're putting pressure on certain water molecules, and they pull on water molecules that are further down in the cup and bring the rest of that water up the straw. So that's something that you might be using right now. You've also exploited cohesion. If you've ever used a siphon to siphon anything, which I don't know how many of you have done that, but it's the same idea. You get water moving and it pulls other water molecules along. Adhesion we've probably seen more often. This is when that water tends to stick to other things with charges. So if you've ever used a paper towel, you've exploited the adhesive nature of water. You can soak things up with a paper towel, right? Water gets soaked up. Non-polar things, things that aren't like water, like oil, which is non-polar, it's a lot harder to get that, clean that up with a paper towel, right? It kind of doesn't stick very well, right? So water tends to stick to itself, it tends to stick to other things. One of the kind of results of cohesion is something we call surface tension. So water molecules tend to stick to themselves. Therefore, it takes some energy to move those water molecules away from each other. It doesn't take very much. So it's not like jumping into a pool of water is not like jumping into a pool of concrete. Those are covalent bonds, and those are really, really strong. These are hydrogen bonds between the water molecules. They're fairly weak, but they're not non-existent. So it does take a little bit of energy to break them. And insects that are not all that massive, that can spread out their weight. You can see this insect has its legs all spread out. Spreading its weight over as many of those hydrogen bonds as possible, that's enough to keep that insect afloat. So if you've ever done a belly flop, you've experienced cohesion. You've spread your weight out over lots and lots of hydrogen bonds and tried to break them all at once. And it hurts, right? But if you narrow down your mass and concentrate it on just a few hydrogen bonds, you don't even notice it. So you can jump into a pool and break those hydrogen bonds really easily. And that's the same reason why boats float. They're spreading out their mass over a wide area. You take that same weight I mean, some boats are really, really heavy. You take that same weight and you concentrate it in one area, it's going to sink. So you spread it out over many hydrogen bonds, it can float. Right? So that's cohesion, leads to surface tension. Water transport in plants, this is also exploiting cohesion and adhesion. So water molecules, basically first they evaporate from the leaves. Because those water molecules are leaving the leaves, it's pulling on water molecules that are in the trunk of the plant or the tree. And those water molecules are pulling on water that's in the roots or out in the soil. So it brings water into the plant. So those are water molecules all sticking together, cohesion. The water molecules also will stick to the sides of the little tubes that are in the plant, and that's adhesion. So that's also due to cohesiveness. All right, so that's the first property of water. And the second property of water is that it's a versatile solvent. So the word solvent, so we have solvent and that's a V, solvent and solute. Solvent is the liquid, and this solute is what you dissolve in the liquid. So this might be the solid. You can also dissolve one liquid in another liquid, so the solute could also be liquid as well. But in general, solvent is your liquid and solute is the solid you're trying to dissolve in the liquid. So one thing that you can easily dissolve in water is something like salt. Salt, remember, NaCl is an ionic compound. So you have Na plus and you have Cl minus. When you put sodium chloride, table salt, into water, the ions in sodium chloride dissociate, so they separate. And water will form what's called a hydration shell around each of those ions. The cation, the sodium, is going to be attracted to the oxygen part of water, and the anion, the chlorine, is going to be attracted to the hydrogen. So here you have, you might not be able to see, but you have chlorine surrounded by water with the hydrogens pointing in, and here you have sodium surrounded by water with the oxygens pointing in. And it keeps them suspended. So this is, you put a little bit of salt in water, it disappears right away. Right? If you keep putting salt into water, eventually you're going to reach a point where all the water molecules are surrounding as many sodium and chlorine molecules as possible. That's called a saturated solution. You add more salt to it, there's now no more water left to bond to the sodium chloride, so the sodium ions and the chlorine ions bind to each other and they sink to the bottom. So that's what happens if you keep adding salt to water. But at first, the salt dissociates and it's suspended, and that's dissolving. So you've probably done something like this. If you've ever had coffee, you've dissolved sugar in water. Same idea. The sugar molecules are separating from each other, and they're being attracted to the water molecules. Is it easier to dissolve sugar in hot coffee or cold coffee? All right, pretty obvious, right? Hot coffee. The reason why is that in order for things to dissolve, to be suspended, to be separated out in a liquid like water, they first have to break free of each other. So in hot coffee, heat is energy. It's going to be breaking the bonds between ions. It's going to be breaking the bonds between those sugar molecules and separating them out and allowing them to dissolve. In cold coffee, you don't have that heat energy to break the bonds initially. So you dump it in. What do you do to get it to dissolve? You stir it. So you're using physical energy. You're actually physically moving and adding that energy to your iced coffee to break apart those sugar molecules. Right? Once they're broken apart, they get surrounded by water. They stay suspended. They're dissolved. Right? Okay. So many different substances will dissolve in water. So it's not only ions, but it's also polar substances. So sugar is a polar molecule. It dissolves in water. Non-polar liquids will not dissolve in water. So oil here is non-polar. It's made up of bonds, covalent bonds that do not share unequally. So if you put vegetable oil into water, it separates out. Have you heard of, all right, well, now I'm blanking on the term, but when you cook, you can get oil to mix with things. Does anyone know how you normally do that while cooking? I don't know if any of you are cooks, really into cooking. But there's times when you have oil and you want it to mix with the liquid or the water. So if you're making a gravy and you want your oils to mix in and not separate out, what you do, you add typically an acid to it, and it actually will change the oil into something that has a little bit of polarity, and it'll cause it to mix. It'll cause it to mix in with the water. Well, baking, you're heating things up and you're changing molecules that way. So, yeah.
So one of them would be, what you just said, it would make it neutral.
Change the polarity of the oil? Yeah, you can. So, and I think that probably happens as well as you're baking, because you're adding a lot of energy there. You're breaking up a lot of the bonds, and so parts of it will start changing their properties. So you do. There's a lot of chemistry to cooking. So yeah. Okay. Let me see. So that's the second one. Okay, so let's move on to this, and then I'll come back to that question. Okay, so water bonds to things, sticks to things. Water is because of that, water is a really good solvent. Third property of water, water regulates temperature. Water resists temperature change. This is because it has what's called a high specific heat. And specific heat is just a measure of the amount of energy required to change the temperature of a substance. So you've probably experienced this if you've ever boiled a pot of water. If you put a pot of water on the stove, you turn on the heat, the metal pot that you put on the stove gets hot really fast, right? But it takes a long time for the water to reach boiling. So you have to wait and wait and wait. And finally, water starts boiling, right? So the metal heats up really quick. Water takes a long time to heat up. Metal has a very low specific heat. Water has a very high specific heat. So because of that, water heats up very slowly. It also cools down very slowly. So it resists change in temperature. So we experience this all the time being in Florida. And basically this part of Florida, we're kind of on an island. We have the Gulf, we have the Atlantic, we have Okeechobee. We're really surrounded by water on all sides. So our temperature throughout the year doesn't change all that often. Like it pretty much, we're in a very narrow range. Where if you go to somewhere that's more inland, they have really, really hot summers and they have really brutally cold winters. So there's a huge fluctuation in temperature. So why does being near water regulate the temperature? So here's kind of a picture of the US, and you can see that on this date, it was January 6, 2014, it was pretty cold inland, so minus 21 here. And if you look near the coast, it's much more moderate. So the same sort of parallel to this area, your same latitude, you've got minus 25, and you've got 54 over here. So why is it so much warmer here than it is here? Well, the reason is that as the Earth cools down, as the land cools down, the water here takes longer to cool down. So water ends up being warmer than the land, and the heat or the energy from the water is drawn off onto the nearby land and keeps it warm. Same thing happens in the summer. The opposite temperatures would be here. This would be really warm, and the water would stay cool, and the heat from the land would be drawn off into the water, and it would keep areas on the coast cooler during the summer. So if you go down to Key West right now, it's a little bit nicer than it is here. So you're a lot closer to the water. You're really surrounded by water. If you go down to Key West in the winter, it'll actually be a little bit warmer than it is here. They're even more moderate than we are. We're still very moderate in comparison to places inland, like here, right? So being near water moderates temperature. It keeps temperatures from getting too cold. It keeps them from getting too warm. Okay. Kind of related to this is why sweating works. So as water heats up, some molecules will be so energized that they will break free. This is called evaporation. So energy causes molecules to move relative to each other. And if they move fast enough, they'll have enough energy to break those hydrogen bonds and leave. As water evaporates from your skin, the remaining water molecules have a lower average energy level than the ones that left. So the highest energy molecules leave. The energy molecules that stay behind have a lower energy level. So the average energy on your skin decreases as evaporation occurs. So, if we just put some numbers on, if we had some that were 100 degrees, some that were 95 degrees, and some that were 90 degrees, the average temperature of those molecules would be 95 degrees. If the 100-degree ones leave, the average temperature is now 92.5. So average temperature has gone down a little bit. And that's what happens when you sweat. You sweat, some of those molecules are so energized they leave, and you're left with less energized molecules on your skin. If you were to sit in front of a fan, it would push those molecules away faster, and that's why you feel really cool if you sweat and then sit in front of a fan. So that's evaporative cooling. It's kind of related to this process. Okay. So just a few more, and we'll see. If we don't get to all of these, we'll finish them up on Friday. Okay, water also expands when it freezes, and some of you may have experienced this already today. If you've ever had ice, you notice that ice floats. So when water is warm, hydrogen bonds between the water molecules are constantly breaking and reforming. As water moves, it's breaking and reforming, breaking and reforming. As water cools, the hydrogen bonds between water molecules will stabilize. And hydrogen bonds actually cause the water molecules to not fit very tightly together. They're actually pushed apart a little bit. And that's because you have positive and you have negative. It needs to arrange itself so the positive are facing the negative, but the positive is not all that close to the other positive. It's going to push those molecules a certain distance apart, and you're going to make this matrix of water molecules like this. So here's liquid water, where the water molecules can actually fit a little bit closer together, and here's ice, where the hydrogen bonds push the water molecules further apart. So most liquids, when they solidify, when they freeze, it actually causes the molecules to come together and fit a little bit more closely together. Not so with water, not so with polar molecules. When they freeze, the hydrogen bonds push them further apart. So ice floats. So this is really something that is advantageous for biological organisms, especially those that live in the Arctic, because if you're a fish and if ice were to sink, ice would freeze at the surface, it would sink down and start filling up from the bottom up, and you'd end up with a solid, the ocean in the Arctic would just be solid ice because it would constantly be freezing on the surface and sinking, right? That's not the way it happens. When ice freezes, it floats, stays near the top, and this allows there to be a layer of liquid water that's actually shielded from the cold outer temperature and stay relatively warm, still pretty darn cold, but relatively warm, and allow fish to survive winters under ice. So this is why we can do things like go ice fishing. So you can drill a hole in the ice and you can stick a fishing rod down and there'll be things living down there. That wouldn't be possible if ice didn't float. So if ice sank, fish wouldn't live in the Arctic. Okay. Okay, there's one more thing. I'm just going to briefly mention it, and then I'll review some of this on Friday when we have a little more time. Water participates in lots of chemical reactions. So chemical reactions is any time two or more molecules swap atoms. So two molecules come together and somehow atoms are swapped between them and rearranged, yields different molecules at the end. Water is involved in most reactions and is often a reactant or a product. So a lot of reactions, especially reactions that happen in biological organisms, occur in water. So it's the substance that they're floating in, and oftentimes we'll see it's a participant. When we look at photosynthesis, it's a major input. For respiration, it's an output. It's a product. So we're going to be talking about a lot of these, but water is hugely involved in chemical reactions. All right. I'm just going to briefly mention this, and I'll probably have to go into this more. This is a property of water, but I know you only have a minute left. pH is something that we'll talk about at the start of class on Friday. pH is a measure of concentration of certain ions in water, and we'll go over the pH scale on Friday, and then we'll continue.